In the heart of modern Rome, beneath the endless flow of tourists and the rumble of traffic, stands a structure that defies every law of architectural decay, the Pantheon. Nearly 2,000 years old, its massive dome still the largest unreinforced concrete span on Earth remains flawless. No cracks, no collapse, no surrender to time. Now consider this. The concrete parking garage built in your neighborhood 30 years ago is already crumbling. Something doesn't add up, does it? The Romans weren't just building monuments. They were encoding secrets into stone and mortar, secrets we've spent centuries trying to rediscover. Tonight, we're going to uncover what made their construction methods so devastatingly effective that their works have outlasted empires, religions, and entire civilizations. We'll examine the engineering brilliance that allowed structures to stand for millennia, explore innovations so advanced they wouldn't be replicated for over 1,000 years, and reveal the chemical mystery hidden inside Roman concrete that modern science only cracked in the last decade. Because here's what most people don't realize. Ancient Rome wasn't just powerful because of its legions or its laws. It was powerful because it built permanence into everything it touched. Let's begin where all great civilizations begin, with the foundations. The roads that conquered continents. Imagine standing at the edge of the Roman Forum in the year 100 AD. You're about to embark on a journey that will take you from the heart of Italy to the farthest reaches of Britannia, over 1,500 miles. You won't get lost. You won't sink into mud during the rainy season. You won't struggle to find your way, because Rome had already paved the path. The Romans understood something fundamental that modern infrastructure planners often forget. Connectivity is power. But they didn't just build roads, they engineered arteries of empire that would pump resources, armies, and ideas across 3 continents. At their peak, Roman roads stretched over 250,000 miles, a network so vast it would take you 10 times around the equator to match it. But here's where it gets interesting. Many of those roads are still in use today, not as museums, not as archaeological curiosities, as functioning roadways bearing the weight of modern vehicles 2,000 years after Roman engineers first carved them into the earth. How? The answer lies beneath the surface literally. Roman road construction was a masterpiece of layered engineering. First, workers excavated a trench roughly 3 feet deep, creating a foundation channel that would prevent water accumulation and soil erosion. Then came the stadamen, a base layer of large flat stones carefully fitted together like a massive puzzle. This wasn't random placement. Each stone was selected for size, shape, and stability. Above this foundation, engineers added the rudis, a thick band of crushed stone mixed with lime mortar, creating a surface that could absorb and distribute weight. Then came the nucleus, another layer of gravel and sand, compacted with such precision that it became nearly impervious to water penetration. But the genius was in the surface itself. The final layer, called the summum dorsum, consisted of precisely cut stone blocks fitted so tightly that a knife blade couldn't slip between them. And here's the detail that separates Roman engineering from everything that came before. These stones were cut with a subtle convex curve. Rain didn't pool. Water drained immediately to carefully constructed ditches on either side. The Romans built roads that cleaned themselves. And there's another element that defined Roman road construction: the obsession with straightness. While other civilizations allowed their paths to meander around obstacles, following the natural contours of landscape, Roman engineers did the opposite. They went through mountains, not around them. They bridged valleys instead of descending into them. They drained swamps rather than circumventing them. Why? Because in the Roman mind, efficiency trumped convenience. A straight road might require enormous upfront labor cutting through hillsides, hauling millions of tons of earth, coordinating thousands of workers. But once complete, it reduced travel time, simplified navigation, and projected imperial power across the landscape like a spear thrust into enemy territory. This wasn't just civil engineering. It was psychological warfare made manifest in stone. Water, the invisible architecture of empire, but roads alone don't build civilizations. You need something more fundamental, something every human settlement has wrestled with since the first permanent structures rose from the groundwater. Ancient cities faced an impossible equation: grow large enough to matter, and you'll outstrip your local water supply. Stay small enough to survive on nearby sources, and you'll never achieve the population density required for cultural, military, or economic dominance. Rome solved this problem with a technology so sophisticated that it wouldn't be equaled until the Industrial Revolution: the aqueduct system. Picture this: over 250 miles of channels, tunnels, bridges, and pipes, all working in concert to deliver fresh water from mountain springs directly into the heart of a city of 1 million people. That's the population of Rome at its zenith. 1 million souls all drinking, bathing, washing, and consuming water that had been transported across vast distances without a single mechanical pump. Let that sink in for a moment. No electricity, no diesel engines, no modern hydraulics. Just gravity, mathematics, and absolute precision in construction. The Aqua Claudia, completed in 52 AD, stretched nearly 43 miles from its source to the city, maintaining a gradient so subtle, just a few inches of drop per mile, that water flowed steadily without eroding the channel or losing pressure. Roman engineers calculated angles with such accuracy that modern surveyors examining these structures are left stunned by their consistency. But the real innovation wasn't just in the channels themselves. It was in how the Romans approached obstacles. When terrain demanded it, they went underground, carving tunnels through solid bedrock using nothing but hand tools, fire, and vinegar. Yes, vinegar. They would heat the rock face with fire until it was white-hot, then splash it with vinegar, causing thermal shock that fractured the stone. Primitive by our standards, perhaps, but devastatingly effective. When valleys stood in their path, they built bridges, some reaching heights of over 160 feet. The Pont du Gard in southern France, a 3-tiered aqueduct bridge, still stands as a testament to Roman structural engineering. It's not just that it survives, it's that it was built without mortar. The stones, some weighing over 6 tons, were cut so precisely they locked together through shape and gravity alone. This is engineering as art form. And here's the part most people miss. Aqueducts didn't just provide drinking water. They liberated labor. Before these systems, thousands of people were occupied daily just hauling water from wells and rivers. With aqueducts, those same hands could be redirected to construction, manufacturing, agriculture, administration. The aqueducts multiplied Rome's productive capacity by freeing its workforce from the most basic survival tasks. Infrastructure isn't just about convenience. It's about unlocking human potential, lifting the impossible, the machines that built mountains. Now we arrive at perhaps the most perplexing question of Roman construction. How did they lift stones weighing several tons each, stack them hundreds of feet high, and do it all without the cranes, pulleys, and hydraulic systems we consider essential today? The answer involves devices so clever that Renaissance engineers would study their principles 1,500 years later, trying to reverse engineer Roman techniques from crumbling ruins. Meet the polyspasto, a compound pulley system that multiplied human strength through mechanical advantage. In its most complex form, this device incorporated 5 separate pulley wheels arranged in a sophisticated configuration. A team of men operating a large wooden drum, essentially a human-powered winch, could lift loads weighing several thousand pounds. But the Romans didn't stop there. For truly massive stones, they developed the pentaspastos and the massive wheel crane. This latter invention was particularly ingenious, a gigantic wooden wheel, sometimes 20 feet in diameter, with men walking inside it like hamsters in an exercise wheel. As they walked, the wheel rotated, winding rope around an axle and hoisting enormous architectural elements into place. Contemporary accounts suggest these machines could lift blocks weighing up to 60 tons. Think about that for a moment. 60 tons. That's the weight of 10 African elephants, suspended in midair using nothing but rope, wood, and human muscle power channeled through mechanical advantage. But lifting was only half the challenge. The Romans also pioneered specialized grips and clamps, the Lewis and the forceps, designed to secure irregularly shaped stones without damaging them. These weren't crude hooks. They were precisely engineered tools that distributed pressure across load-bearing points, preventing fractures during the lifting process. What we're looking at here isn't brute force. It's applied physics refined through centuries of trial, error, and incremental improvement. The arch. Turning weight into strength, the Romans didn't invent the arch. That credit likely belongs to the Mesopotamians, or perhaps the Egyptians. But the Romans perfected it, weaponized it, and turned it into the foundational element of structures that would define Western architecture for 2 millennia. Here's why the arch matters. In traditional post and lintel construction, 2 vertical supports, with a horizontal beam across the top, there's a hard limit to how wide you can span before the weight of the beam causes it to crack and collapse. Stone is incredibly strong in compression, but tragically weak in tension. A stone lintel pulls itself apart under its own weight. The arch solves this by converting all those destructive tensile forces into compressive ones. Every stone in a properly constructed arch is being squeezed, not pulled. And stone loves being squeezed. It can withstand enormous compressive loads without failing, but Roman engineers took this principle further. They realized that if you rotate an arch through 3-dimensional space, you get a vault. And if you rotate it completely around a central point, you create a dome, a structure that can span vast distances without any internal supports whatsoever. The Pantheon's dome stretches 142 feet across. For context, that's wider than the dome of the United States Capitol building. And unlike the Capitol, which is reinforced with steel, the Pantheon's dome is pure concrete and brick, standing freely without a single metal support beam. This was structural engineering as intellectual achievement proof that understanding principles matters more than possessing advanced materials. The Romans also innovated the segmental arch, a flatter, more subtle version of the traditional semicircular form. This allowed them to build bridges with much lower profiles, crossing rivers without the massive height clearances that semicircular arches required. The Limera Bridge in Turkey, with its 26 segmental arches stretching nearly 1,000 feet, maintained such a low profile that it wouldn't be surpassed in design sophistication for an entire millennium. These weren't just functional structures. They were declarations, statements carved in stone that announced Roman technical supremacy to every eye that beheld them. The hidden systems, heating, sewers, and sawmills. But let's descend from the monumental and examine the practical innovations that made Roman daily life not just possible, but comfortable technologies so advanced they would vanish from Europe after Rome's fall and not return until the modern era. Consider the hypocaust system, the world's first central heating technology. In Roman bathhouses, villas, and public buildings, engineers raised floors on small pillars of stacked tiles, creating a hollow space beneath. A furnace in an adjacent room would heat air, which would flow through these cavities, warming the floor from below. The hot air would then rise through channels built into the walls, heating the entire structure. This solved 2 critical problems simultaneously: It provided warmth without open flames in living spaces, and it eliminated the deadly smoke that plagued earlier heating methods. Romans could enjoy heated rooms without risking death by asphyxiation, a genuine revolution in domestic comfort. Then there's the Cloaca Maxima, Rome's great sewer. Initially built to drain local marshes, this system evolved into a comprehensive sewage network that channeled waste away from population centers. The main tunnel was large enough for 2 horse-drawn carts to pass each other, roughly 10 feet wide and 13 feet tall. It wasn't just a drainage ditch. It was an underground highway for waste. What's remarkable is that the Romans understood something about urban planning that many civilizations would forget. Disease spreads through water. By keeping wastewater separate from drinking water, channeling it away from residential areas, and maintaining consistent flow through engineered gradients, they created urban environments far more sanitary than medieval European cities would be 1,000 years later. But perhaps the most overlooked Roman innovation was the water-powered sawmill. In the ancient city of Hierapolis, modern-day Turkey, archaeologists have confirmed the existence of a mill powered by a water wheel, using a crank and connecting rod mechanism to drive reciprocating saws. This allowed the rapid, precise cutting of marble and wood materials essential for large-scale construction. This wasn't just useful, it was revolutionary. Before mechanization, cutting large marble blocks required days of manual labor with hand saws. The water mill could accomplish the same task in hours, freeing up human workers for skilled tasks, while machines handled the repetitive, physically demanding work. It's a principle we think of as modern, letting machines amplify human capability. The concrete enigma, a chemical mystery solved, and now we arrive at the centerpiece of Roman construction genius. The material that made everything else possible, concrete, not the concrete we use today, mixed from Portland cement in factories and poured on construction sites. Roman concrete was something different, something that in crucial ways was actually superior to our modern formulations. The base recipe was deceptively simple: volcanic ash, lime, seawater, and aggregate stone. Mix it together, pour it into wooden forms, let it cure. But the results were anything but simple. Roman maritime concrete used in harbor structures, breakwaters, and seawalls. Modern concrete and marine Roman structures get more durable with age. For decades, scientists were baffled. They could analyze the chemical composition, but they couldn't understand why it performed so differently from modern concrete. The answer, discovered only within the last decade through advanced mineralogical analysis, lies in a chemical reaction that occurs between the lime, volcanic ash, and seawater. When seawater infiltrates Roman concrete, it doesn't erode the structure. Instead, it triggers a crystallization process that creates new mineral compounds, specifically a rare mineral called aluminum tobermorite. These crystals grow within the concrete matrix, filling microscopic cracks and actually reinforcing the material from within. It's self-healing concrete, and the Romans didn't need laboratories or electron microscopes to develop it. They needed observation, experimentation, and a willingness to refine techniques across generations. But there's another element that recent research has highlighted: lime clasts. For years, these small, bright white chunks found throughout Roman concrete were dismissed as signs of poor quality control, evidence that the lime wasn't properly mixed into the concrete. But scientists now believe these were deliberately added. When microscopic cracks form in the concrete and water seeps in, these lime clasts dissolve slightly. The Romans built self-repair mechanisms into their concrete at the molecular level. Modern concrete is designed to be inert. We want it to set quickly, harden completely, and remain chemically stable. Roman concrete was designed to remain chemically active, constantly adapting to its environment and repairing minor damage before it could propagate into structural failure. This is the difference between building for decades and building for millennia. The architecture of eternity. There's a deeper principle at work in all of these innovations, something that goes beyond specific techniques or materials. The Romans built with permanence as the primary design criterion. Look at how they approached construction sequencing. Unlike builders who might erect a structure and add decorative elements simultaneously, Roman engineers separated these processes. First, they built the structural core walls, arches, foundations, using the most durable materials and techniques. Only after the skeleton was complete and fully cured did they add marble facades, ornamental details, and artistic flourishes. This modular approach meant that even if decorative elements were damaged or removed over centuries, the structural integrity remained intact. The Colosseum lost much of its marble cladding during the Middle Ages, scavenged for other building projects, but the underlying concrete and stone core still stands. They weren't building for their generation. They were building for civilizations that didn't yet exist. This mindset extended to quality control. Roman construction sites operated under strict oversight, with specialized teams responsible for specific tasks. Stonemasons didn't do carpentry. Concrete specialists didn't lay roads. Each craft maintained its own standards, techniques, and traditions. This created a culture of expertise where knowledge was preserved and refined across generations. When a Roman engineer designed a bridge, he wasn't inventing from scratch. He was drawing on centuries of accumulated knowledge, every failure studied, every success analyzed, every technique optimized through countless iterations. This is what modern project management tries to replicate with quality assurance protocols and specialized contractors. The Romans simply understood it intuitively. Lasting quality requires specialized knowledge and unwavering standards. The lessons we forgot after the Western Roman Empire collapsed in 476 AD, many of these technologies vanished from Western Europe. The hypocaust system disappeared. Aqueduct construction ceased. The formula for durable concrete was lost. For nearly 1,000 years, European builders would construct with less sophistication than their Roman predecessors. Why? The knowledge was there, preserved in structures still standing. But knowledge isn't just about having information available. It requires the institutions, economic resources, and political stability to implement it. The fragmented kingdoms that emerged from Rome's ashes lacked the organizational capacity, the surplus labor, and the long-term planning horizons that Roman construction required. You can't build an aqueduct if your kingdom might not exist in 10 years. You can't invest in concrete research if you're focused on immediate survival. So the techniques faded, remembered only in the crumbling monuments that dotted the landscape, reminders of capabilities lost. It wasn't until the Renaissance, when European scholars began systematically studying Roman ruins, that some of these methods were rediscovered and refined. The revival of concrete construction in the 18th century, the reintroduction of central heating in the 19th century, the modern understanding of arch mechanics. We've spent the last 500 years relearning what Rome knew 2,000 years ago, building beyond tomorrow today. When architects design buildings, they typically calculate a service life of 50 to 70 years. Commercial structures might be planned for a century at most. We accept demolition and reconstruction as inevitable parts of urban development. The Romans would have found this incomprehensible. Every structure they built was intended to outlast not just the builders, but their children, their grandchildren, and countless generations beyond. This wasn't arrogance. It was philosophy made tangible. The empire was eternal, therefore. Its physical manifestations should be too. Obviously, the empire wasn't eternal, but their buildings were. And that's the paradox that makes Roman engineering so fascinating. Political structures collapse. Languages evolve, religions rise and fall, entire ways of life disappear, but stone and concrete remain. The Pantheon has outlasted paganism, survived the Christianization of Rome, endured wars, earthquakes, and centuries of weather. It now serves as a church, hosting millions of visitors annually, still using the same dome poured nearly 2,000 years ago. There's something profound in that persistence. These structures have witnessed more human history than any document, any story, any living tradition. They are history made solid proof that human beings, when they commit to excellence and permanence, can create works that transcend their own mortality. The ingredient of intention. So what was the true secret of Roman construction mastery? It wasn't just the volcanic ash, though that helped. It wasn't merely the engineering principles, though those were crucial. It wasn't only the organizational systems, though they enabled everything else. The secret was intentionality. The Romans built every structure as if it would need to stand for 1,000 years, because in their worldview, it would. They didn't cut corners. They didn't accept good enough. They invested enormous resources, time, and expertise into construction because they believed that what they built would define their civilization long after they were gone. And they were right. When tourists stand before the Colosseum, they're not thinking about Roman politics or economic systems. They're experiencing the tangible reality of a civilization's capabilities. When engineers study the Pantheon Dome, they're confronting evidence that ancient builders understood principles that modern technology has only recently allowed us to fully analyze. The buildings are the legacy. Everything else, the emperors, the conquests, the laws we know about, because the structure survived to tell the tale. What we can build, this brings us to an uncomfortable question. What will our civilization leave behind? In 2,000 years, will there be structures from our era still standing, still functional, still impressive? Or will archaeologists of the future dig through compacted rubble and wonder why we built everything to last less than a human lifetime? The Roman example suggests that durability isn't just about materials or techniques. It's about values. It's about believing that what we create today matters for people we'll never meet and times we can't imagine. Perhaps that's the most important lesson Roman concrete can teach us, not just how to mix lime and volcanic ash, but why we should care about building things that outlast us. Because in the end, civilizations aren't judged by what they consume, but by what they create. Not by what they use up, but by what they leave behind. The Romans left us monuments that still inspire wonder 2 millennia later. What will we leave for the civilizations that come after us? If this exploration into the engineering genius of ancient Rome has captivated you, subscribe for more deep investigations into the technologies, mysteries, and innovations that shaped human history. Because the past isn't just about what happened. It's about understanding what's possible. And sometimes the oldest lessons are the ones we need most.